Hello everyone, my name is Roy and I'm a PhD candidate at the Technion. Today I will present our paper Web Table Retrieval using Multimodal Deep Learning. This work was done during my research internship in IBM Research. In this paper, we look at web tables as multimodal objects. As an example, we extracted a table from Wikipedia that describes the different continents. We focus on 4 properties which represent the different modalities of a table. The table has a schema, it has records, it has columns or facets, and finally, it has a description in the form of page title and caption. Originated in the database community, table retrieval is a fairly new task. Most works have looked at tables as text documents and enhanced the representation using semantic and similarity-based features. In our work, we automatically extract hidden features using neural networks. Neural networks are not new to multi-field documents in information retrieval, and was recently suggested by Zamani et al. In 2018. Yet, in our work, we take advantage of the fact that each of the modalities has its own unique structure that should be taken into account. In this work, we further make a novel use of GMUs, Gated Multimodal Units. In this work, we consider more than 2 modalities at once. Finally, co-learning in information retrieval is usually done by combining several similarities or several rankings. However, in our work, we use helper labels to enhance the learning process. This is our proposed approach to table retrieval. We term this approach Multimodal Table Retrieval, or MTR. MTR has 5 main components, namely the input representation, the encoding, the priors, the unimodal, and finally the multimodal. Now, I will guide you through the architecture of our system, starting with the input representation. As I mentioned before, we look at 4 different table modalities. Looking at the description, the tokenization is straightforward, as it is expressed in natural language. So the tokens will be continent, area, and population. The schema, however, has a structure. Specifically, to allow the network to learn this structure, we suggest a new token. We term this token EOC, end of column. This token is inserted between the different columns of the schema, allowing the network to understand and capture the meaning of the different columns. Looking at the records, we further suggest a new dimension. This dimension we suggest to capture with an additional token called EOR, end of row. Finally, the representation of these facets is fairly similar. However, for the facets, we process the table by columns rather than by rows as we do for the records. Once we have the input representation, we can now move forward to the encoding. In the encoding phase, we utilize the unique characteristic of each of the modalities. When we look at the query and the description, we use RCNN, which is designed to handle natural language text. However, for the schema, which is not represented in natural language, we use a multi-layer perceptron. Finally, for the records and for the facets, we use a three-dimensional CNN. Recall that in addition to the row dimension and to the column dimension, each of the tokens that represent the data has a multi-dimensional embedding. In this work, we use glove, but glove can be replaced with BERT, Elmo, and whatever language model you prefer to encode the tokens themselves. We now move forward to the final part of MTR. In this part, we use GMUs. GMUs are a gating scheme for learning a multimodal joint representation. Specifically, in our work, we use the GMUs to represent multimodal table using the different modalities and to represent the table query combination. We further create helper labels based on each of the modalities by themselves. In addition, we use the query by itself to extract a query prior relevance label. And finally, we use unimodal query relevance labels to represent the unimodal and query priors. Using these helper labels, we employ a co-learning technique. This is how the final part of our framework would look like without co-learning. Using a GMU, we obtain a multimodal table representation from the four modalities we have. Using an additional GMU, we create a query table representation and generate a single relevance estimation over it. Extracting helper labels, we further create 9 additional labels, which can be used as a part of our loss function to enhance the learning of our main relevance estimation. As we can see here, the loss function is a weighted function that uses the different labels losses. To evaluate our framework, we first use a standard benchmark called Wikitables, suggested by Zhang et al. In 2018. The Wikitable benchmark contains 60 ad hoc queries, and for each of these queries, we have a pool of candidate tables. In our work, we further suggest a new publicly available benchmark for the table retrieval task, based on natural language queries. This benchmark was created using the Google Natural Questions dataset, from which we extracted questions that have a table as an answer. The first benchmark has 60 queries, and our newly suggested benchmark has 610 natural language queries. The grades for the Wikitables are threefold, so we have irrelevant, relevant, and highly relevant. And in the GNQ tables benchmark, we have a binary grade. We have irrelevant and relevant. This is a result of taking the table as a single answer to a specific query. We evaluated our solution against several baselines, including the state-of-the-art suggested by Schraga et al. In 2020, and the state-of-the-art in neural multimodal retrieval suggested by Zamani in 2018. As we can see from the tables, MTR achieves better ranking quality than all the baselines on both benchmarks. In order to test the different components of our framework, we conducted an ablation study. The first component we analyzed is the effect of co-learning. To do so, we discarded different kinds of helper labels from the main loss function and evaluated the resulted relevance estimation. As we can see, using co-learning obtains much better results. For the Wikitables, the measures are differently affected by the different segments. However, when we look at the G and Q tables, we see a clear pattern indicating the importance of prior helpers, and the query unimodal helpers. This may be explained by informativeness that natural language queries hold. Then we analyze the effect of the different modalities by evaluating the helper labels by themselves and by discarding a single modality at a time from the co-learning process, as we can see here. Clearly, using all the modalities on both benchmark achieves much better ranking quality. Specifically, for Wikitable, we observe that the record modality, as we can see here, the records modality as a standalone achieves the best result. However, for the G and Q table benchmark, we see that the schema modality has the best result. This suggests that when we have less training data, as in the case of Wikitables, the importance of the content of the table itself as it captured by the records is very important to assess the relevance. However, when we have sufficient training data, as in the case of the G and Q tables, the schema is much more valuable. Finally, we highlight 5 queries for each dataset to illustrate the modality-driven intents. For example, having a query USA population by state mostly addresses the schema, as most probably the attributes of the relevant table would include the attributes such as population or state or similar terms to that. When we look at a query such as household chemical strength, then the entities included in the records is much more important in order to achieve a relevant table. Finally, if we look at queries such as how many gold medals did Australia win in the 2000 Olympics, then the description becomes highly beneficial, since the description holds the total information that is included in the table, as we see. To sum, we model web tables as multimodal objects. We further suggest a novel deep multimodal learning approach for the web table retrieval task. Our proposed approach makes a novel use of GMUs over 4 different modalities. It further employs a co-learning technique using a set of helper relevance labels. In this work, we further suggest a new dataset for the web table retrieval task, which we call G and Q tables, and holds natural language queries for tables. Finally, we show that our approach achieves a much better ranking quality than strong state-of-the-art baselines. Thank you very much for listening. And if you have any questions, I'll be available here in the Zoom session to answer questions, and I'm available in this email and this web address if you have any offline or other suggestions or questions. Thank you very much and have a nice day. Bye-bye.